So, hello friends. So, welcome to a lecture series on nonlinear programming. So, we are dealing with geometric programming problems. We have seen that if we have highly nonlinear problem having negative powers or powers in fractions, then how can we find the optimal solution of such problems? What we have seen that if we have a unconstrained optimization, I mean problem without any constraint, then how can we find the optimal solution, and how can you find optimal solution for the problems with constraint optimization, constraint equality optimizations we have to deal with. Now, in all those problems, the coefficients we have assumed they are positive. All the coefficients in all the terms we assume that they are positive. Now, how can we solve those polynomials having negative coefficients? So, that we will deal in this lecture. First, we will see how can we solve a problem having a degree of difficulty more than 0, that is 1, suppose. Okay. Now, suppose this is a problem is minimization of f, which is equals to 2x1 x2 plus it is 2x1 x2 raised to power minus 1 x3, okay, plus 4 x1 raised to power minus 1 x2 raised to power 2 and x3 raised to power minus 1 by 2, subject to the constraint is under root 3 x1 raised to power minus 1 plus 3 x1 raised to power minus 1 x3 raised to power, it is x3 raised to power minus half less than equals to 1 and x1 x2 x3 greater than 0. So, let us consider this problem. Okay. Now, in this problem how many terms we are having? We are having 1, 2, 3, 4, 5 terms. Okay. And how many variables we are having? We are having 3 variables x1, x2 and x3. So, the degree of difficulty for this problem is, degree of difficulty will be the total number of terms in the objective function as well as in the constraints, that is 5, 1, 2, 3, 4, 5. How many variables? Variables are 3, that is minus 3, minus 1. This we have already shown in the last lecture that degree of difficulty is equal to total number of terms in the objective function and in all the constraints minus number of variables, number of unknowns minus 1, that will be the degree of difficulty. So, degree of difficulty in this for this problem is 1. Now, degree of difficulty is 1, this means this problem if we solve will involve less number of, I mean the gap of the variables and the constraints will be 1. That means the constraint which we are having with respect to deltas will be having many solutions. Okay. So, how we will form that problem? That will be maximizing G delta. Okay, G delta. Now, the first coefficient is 2. So, it is 2 upon delta 1 whole raised to power delta 1. It is 2 upon delta 2 whole raised to power delta 2. The third term is 4 upon delta 3 whole raised to power delta 3. Next term is under root 3 upon delta 4 whole raised to power delta 4, and next term is 3, which is 3 upon delta 5 whole raised to power delta 5, and lambda raised to power lambda, where lambda is delta 4 plus delta 5. Lambda is corresponding to the constraint. We have delta 4 and delta 5. So, it is lambda equal to delta 4 plus delta 5. Okay. Subject to what are the conditions? Now, see the conditions. Okay. Now, corresponding to x1, if we take delta 1, so the power here is delta 1, here it is delta 2 because it is having 1 power, 1 into delta 2 is delta 2, here it is minus 1 power, so it is minus delta 3. So, it is delta 1 from here plus delta 2 minus delta 3, and it is minus delta 4 minus delta 5 is equal to 0. So, that will be the first constraint. Okay, that will be first constraint. Now, sorry, it is x2. In the problem it is x2 raised to a minus 1. So, delta 4 will not be here, will not be in the constraint. Okay. Now, corresponding to x2 it is delta 1. Okay. Then it is from the next term what we are having, minus delta 2. Okay. Here it is plus 2 delta 3, then here it is minus delta 4 equal to 0. Okay. Now, from the next constraint corresponding to x3 there is no term here, here it is one term, so it is delta 2, then here it is minus 1 by 2 delta 3, then here no term of x3 and here it is minus half, so it is minus 1 by 2 delta 5 is equals to 0. And of course, delta 1 plus delta 2 plus delta 3 equals to 1. Correspond to a constraint, objective function. Corresponding objective function we are having 1, 2, 3 terms, delta 1, delta 2, delta 3. So, sum of these 3, delta 1 plus delta 2 plus delta 3 should be 1, and all delta I must be strictly greater than 0 for all I. These are the system of equations which we are having. Now, in these equations we are having 5 unknowns, delta 1, delta 2, delta 3, delta 4 and delta 5, and we are having 4 equations. So, it will be having many solutions, as we have already seen by finding its degree of difficulty. Since degree of difficulty is 1, so we will be having less equations and more unknowns, infinitely many solutions. Now, what we will do, we will, since it is having many solutions, we will try to express all the deltas in terms of one delta, say delta 5. Okay. So, as we have already solved this problem, you can see here we have first find G delta. G delta is the same expression which we have discussed here, subject to these number of equations. So, we are having 4 equations with 5 unknowns here. So, we will express all the delta i's in terms of delta 5. So, after solving, after expressing in terms of delta 5, we will obtain delta 1 equal to delta 2 equal to 1 plus delta 5 by 4, delta 3 is equals to 1 minus delta 5 by 2, and delta 4 equals to 1 minus delta 5. Okay. This we can obtain very easily by solving these equations. Now, then we will substitute all these values of delta 1, delta 2, delta 3 and delta 4 in G delta. Okay. In this expression we will substitute all the values of deltas. Okay. Then this function will be only in one variable, that is delta 5. Now, this is to maximize. In order to maximize, we are having only now this function, this G delta is in only one variable. So, you take the log both the sides, differentiate with respect to delta 5, find the maximum value of G delta. When we do all this process, we get delta 5 equals to 1 by 2. Okay. And as we got delta 5 equals to 1 by 2, substituting these values in all these expressions over here, we will get delta 1, delta 2, delta 3 and delta 4. So, the minimum value of f, which is equals to maximum value of G delta, which we already know, is nothing but 32. How we obtain 32? By substituting the values of delta 1, delta 2, delta 3, delta 4 and delta 5 over here and lambda over here. When we substitute all these values over here, we got the maximum values of G delta, which is same as minimum value of f. Okay. Now, how to find variables? How to find that? Now, we use equality condition. Okay. From the equality condition, we know that this is our u1, the first term, this is u2, this is u3. So, we know that from the equality constraint, that u1 upon delta 1 should be equals to u2 upon delta 2 should be equals to u3 upon delta 3, and that should be equals to, now if A upon B is equals to, if A upon B is equal to C upon D is equals to E upon F, so that is also equals to A plus C plus E upon B plus D plus F. So that is also equal to this term plus this term plus this term, which is nothing but the minimum value of F, okay, which is 32 as we have already obtained, and in the denominator delta 1 plus delta 2 plus delta 3, which is 1, so it is 1, okay. And from the next condition, from the constraint, under root 3 into x to ratio minus 1 upon delta 4 is equals to 3 x1 ratio minus 1 x ratio minus half upon delta 5 should be equals to, now this plus this, as A upon B is equal to C upon D is equal to A plus B upon B plus D, it is equal to this plus this, which is equals to 1, because this optimality, this optimal solution will be obtained when equality holds. So it is equal to 1, and is equals to, and denominator delta 4 plus delta 5, which is lambda, okay. Now using this equality constraint, we can easily find out the value of x1, x2 and x3, which are x1 equals to under root 3, x2 equals to 2 under root 3 and x3 equals to 12. So this will be the optimal solution of this problem, okay. So that is how we can solve those problems having degree of difficulty more than 0. If degree of difficulty is 0, in that case we will be having, suppose, n number of variables and n number of equations, that is a unique solution. So in that case there is no need of maximizing z delta, since the value of z delta is unique. So that itself will be the value of minimum of f. However, if degree of difficulty is more than 0, so we have to find out the maximum value of g delta by differentiating g delta with respect to the unknown variable, okay. Now how to solve a general polynomial optimization, I mean how to solve a problem having negative coefficients. So we have generalized polynomial optimization is applicable for the problems involving negative coefficients also. To solve such problems, we introduce signum function so that the terms of negative coefficient reduces to the problem with positive coefficient, okay. So to solve such problems having negative coefficients, so only those terms involving negative coefficient we involve a term signum function, so that term become positive, okay. Suppose we have this problem, okay. So how to solve this problem, let us see. So this problem is minimum of f, which is equal to, it is minus 12 x1 raised to power minus 3 x2 square plus, it is 4 x1 raised to power minus 3 x2 cube plus, and it is 3 x1 raised to power minus 1 minus 4 and x2 raised to power square, x2 square. So subject to x1 x2 greater than 0. So it is unconstrained optimization, okay, and this term is negative, this term is having negative coefficient. Now what is degree of difficulty of this problem? Now we are having 3 terms, 1, 2, 3, 3 terms we are having, and how many unknowns? 2 unknowns, x1 x2. So degree of difficulty will be 3 minus 2 minus 1, that is 0. Degree of difficulty is 0, that means we will be having unique solution for g delta, and we are having unique solution. G delta means that the value of g delta will be the value of minimum of f, okay. Now how to solve such problems, let us see. we first find maximum of G delta, which is given as, now it is having negative coefficient which is minus 12. So, in minus 12 we will take minus delta to encounter this negative sign to make this positive. Okay. So, so for this term we are taking negative delta 1, minus delta 1. Okay. This is positive coefficient, so we take delta 2 plus delta 2. This is positive coefficient, so we take plus delta 3. Okay. So, this we will do only for those terms having negative coefficients. Okay. So, it is minus delta 1, then 4 upon delta 2 whole raised to power delta 2, and 3 upon delta 3 whole raised to power delta 3. Now, to encounter this minus delta, because we are introducing it minus delta to make minus 12 positive. So, what will be the change in this function? The change is only this, that we multiply this by rho and raised to the power rho, where rho is either plus 1 or minus 1. Okay. To encounter this effect, we multiply and raised to power by rho, okay, where rho is either plus 1 or minus 1. Now, subject to what are the conditions? Again, for this term we are having minus delta 1, for this term we are having plus delta 2, and for this term we are having plus delta 3. Now, correct the coefficients of x1. For x1 it is 3 delta 1, because minus 3 delta 1 minus 3 into minus delta 1, that is 3 delta 1. Here it is minus 3 delta 2, because delta 2 is positive, plus delta 2, and here it is minus 4 delta 3, which is equal to 0. Now, for the second term variable x2, we are having minus 2 delta 1, because it is 2 into minus delta 1, because corresponding to this term we are having minus 2 minus delta 1. Okay. And for this term we are having plus 3 delta 2 plus 2 delta 3 equal to 0, and of course minus delta 1 plus delta 2 plus delta 3. Instead of delta 1 we are having minus delta 1. Okay. Now, this is sigma, which may be plus 1 or minus 1. Okay. And all delta i's are strictly greater than 0. Now, here we are having 3 equations with 3 unknowns, unique solution, and that unique solution will give the value of maximum z, maximum of g delta, which is equals to minimum of f, and using the equality constraint we can easily obtain the value of the unknowns. Okay. So, solution is here. You see that we can find maximum of g delta, which is given by this expression, where rho is plus 1 or minus 1, subject to these conditions. Now, we can take rho as either plus 1 or minus 1. Suppose it is plus 1, then we get delta 1 as minus 6, delta 2 is minus 2, and delta 3 is minus 3, that you can easily verify. Okay, you can substitute rho as 1 there and solve these 3 equations. You can simply see that these are the values of deltas we are obtaining, which is not possible. Why it is not possible? Because all deltas must be greater than 0 as per this condition. Okay. Now, take rho equals to minus 1, because rho can take only 2 values, either plus 1 or minus 1. Plus 1 does not give a feasible point, feasible solution. So, we take the another option, that is we take rho as minus 1. If we take rho as minus 1 and solve these 3 equations, we will get delta 1 as 6, delta 2 as 2, and delta 3 as 3. Okay. You substitute these values in the expression of g delta, we can obtain the maximum value of g delta as minus 16, which is same as minimum value of f. Okay. Now, how we will obtain the optimal solution? By applying equality condition. Now, here what will be equality condition? Let us see. Here, what is the first term? First term is minus 12 x1 raised to power minus 3 x2 square upon, now corresponding to this term we are having minus delta 1. So, it is minus delta 1 equals to, it is 4 x1 raised to power minus 3 x2 raised to power 3 upon delta 2, because corresponding to this term we are having plus delta 2, and for the third term it is 3 x1 raised to power minus 4 x2 square upon delta 3. Again this is equals to, this is something a upon b equal to c upon d equal to e upon f, which is equals to a plus c plus e upon, that is sum of the numerators and the sum of the denominators. Sum of the numerator is equals to minimum of f, which is minus 16 as we already obtained, and minus delta 1 plus delta 2 plus delta 3 is rho, and rho is minus 1. Okay. For minus 1 we are obtaining the solution, we are getting the solution. So, this is nothing but 16. So, we are having this delta 1, delta 2, delta 3 already know, we already know the values of delta 1, delta 2 and delta 3. So, solving this and put equal to 16, we can easily find the values of x1 and x2. So, x1 is half and x2 is 1, you can easily check. Okay. So, in this way we can easily get the optimal solution of such problems. Now, this is unconstrained polynomial optimization with negative coefficients. How can we solve a problem having negative coefficient and having constraint also, that is constrained polynomial optimization with negative coefficients. So, what is the problem? Let us discuss the problem. It is minimum of f, which is equals to, it is 2x1 x2 x3 plus is x1 raised to power minus 1 x3 raised to power minus 1 subject to, it is x1 square x3 raised to power minus 2 minus x2 and x3 raised to power minus 2 less than or equals to minus 1 and x1 x2 x3 greater than 0. So, I am simply giving the outline of how to solve the problem, okay, and you can simply solve the system equations and you can easily find out the values of deltas. When you find out the value of delta, this will give the value of maximum G delta, which is equals to minimum of f, and using the equality condition you can easily find the values of the unknowns. Okay. Now, here here this is negative. Okay. How many terms we are having? 1, 2, 3, 4. 4 terms we are having. How many unknowns? 3 unknowns. So, degree of difficulty will be 4 minus 3 minus 1, that is 0. So, degree of difficulty is 0, that means unique solution. Okay. Now, how to solve it? So, we find maximum of G delta, which is equals to, the first coefficient is 2. So, it is 2 upon delta 1 whole raised to power delta 1, it is positive. So, we take plus delta 1. Now, it is also positive 1. So, it is 1 upon delta 2, delta 2. The third term is again positive coefficient. So, it is 1 upon delta 3 whole raised to power delta 3. Now, it is minus 1. So, we take minus delta 4 corresponding to this term. Okay. So, it is minus 1 upon minus delta 4 whole raised to power minus delta 4. Now, this is minus 1. So, what we do, we take rho 1 as minus 1, where rho 1 is this term. Okay, we assume. Now, this into sigma whole raised to power sigma, where sigma is either plus 1 or minus 1, and for the constraint polynomial optimization we are also having a term lambda raised to power lambda. Okay. So, lambda raised to power, here it is rho 1 lambda, because this is negative. Okay. Whatever term we are having, it is plus 1, so it is plus 1, and if it is minus 1, so it is minus 1. Okay. and subject to what are the conditions. Let us see the conditions also. So, coefficient that is power of x1. Power of x1 here is delta 1, here it is minus delta 2, here it is plus 2 delta 3, and here no term of x1, so it is equal to 0. Now for x2, x2 is delta 1, no term here, and here it is plus 2 delta 3, and here it is minus delta 4 because here we are taking the term as minus delta 4. Then x3, x3 is delta 1 minus delta 2 minus 2 delta 3 plus 2 delta 4 equal to 0, as this is minus 2 delta minus 2 multiplied by minus delta 4, which is plus 2 delta 4, that is equal to 0, and delta 1 plus delta 2 is equals to rho, where rho is either plus 1 or minus 1, delta 1 plus delta 2, and delta 3 plus delta 4 is equal to rho 1 lambda, where rho 1 is minus 1, okay, and all delta i's are strictly greater than 0 for all I. Delta 1 minus delta 4, sorry, because it is minus delta 4, cross point to this. Okay. Now, if you see these equations, okay, so these are 4 equations, 4 unknowns, okay, that means unique solution. So, solving these, first you take rho as suppose plus 1, you find the values of deltas. If all deltas come out to be positive, that means you are getting the solution, okay. If deltas come out to be negative, some or all, then we take rho as minus 1 and again solve the problem, okay, solve the system of equations. So, for once you get the values of delta all positive values, you substitute it over here, you get the values of maximum of G delta, that will be equals to minimum of F, and using equality constraint you can get the optimal solution of the problem. Okay. So, that is what the solution gives. Now, when you let rho as plus 1, so you get the values of deltas as delta 1 equals to 1 by 3, which is equal to delta 4, delta 2 equal to 2 by 3, delta 3 1 by 6, and lambda is also 1 by 6, you can easily verify, and minimum of fx is equals to maximum of g delta is equals to 3. Okay. Now, from the equality condition, now you see, if you see the equality condition, that is u1 upon delta 1 is equals to u2 upon delta 2, that must be equals to the sum of numerator and the sum of denominator. Sum of numerator is m is the maximum, minimum value of f, okay, we are calling it capital M, which is 3 here, and sum of delta 1 plus delta 2 is rho, okay. So, it will be m upon rho, you see it is when you apply here, it is 2 x1 x2 x3 upon delta 1 is equals to x1 is to minus 3, x3 is to minus 1 upon delta 2, which is equals to m upon rho, the sum of numerator and the sum of denominator, which is also equals to rho m upon rho square, and rho square is always 1 because rho is either plus 1 or minus 1. So, it is nothing but rho m, and m is here for this example m is 3. Now, similarly, when you take the term corresponding to the constraint, you take the sum of the numerator is minus 1 here, and sum of the denominator is minus lambda. So, minus cancel out, it is 1 upon lambda, you already know it is 1 by 6. So, you will be having this system of equations by which you can easily find out the values of x1, x2 and x3, which are 1 by under root 2, 1 by under root 2. So, that will be the optimal solution of this problem. So, that is how if we have complicated non-linear programming problems. So, some of the problems can be solved using geometric programming approach. If we have some fraction power or negative power or higher powers, constraint or unconstrained problems. So, that can be solved simply by using arithmetic geometric mean inequality. Okay. So, that is how we can easily solve some non-linear problems using this approach. So, thank you very much.